In the last video, we finally finished building and testing all logic sections of our retro printed circuit board. In this video, we'll test HDMI support, try out the other power options, and finally stick this thing into the cabinet. I'm still waiting for some of the widget stuff to come in, so we'll go over that in a subsequent video. When we started looking into adding advanced video, we discovered that the line rate was about 1/2 of what we needed for VGA. Adding VGA support is possible, but not without a lot of logical changes, which we want to avoid. Looking around further, we found RGB to HDMI. If you recall from part 16, RGB to HDMI was born from a desire to connect legacy computers and game consoles to modern monitors. This is implemented in custom hardware and software for the Raspberry Pi Zero. In that last breadboarding session, we built a 5-chip sideboard to convert our UI signals to the proper inputs for RGB to HDMI. For external video support in general, we added this UI connector that contains all of the signals you would need to generate off-board video. We then stuffed those 5 chips into a 16 Victor 8 type PLD and dropped it onto unused site Able2. If you want to roll something of your own, the UI connector is available. If you want an easy way to connect this to an RGB to HDMI setup, then you can simply burn a PLD. For RGB to HDMI support, we just need to add the 6x2 pin header jack 106, the 1x2 pin header jack 107, and a 20-pin socket for the PLD. The 2-pin header is for optionally powering the Pi and daughter card from the Retro. I designed and printed a cheap mount for this. Plug in the connector. Pin 1 is clearly marked, but make sure pin 1 is to the right on your cable. I didn't take a look to see if plugging this in backwards would elicit the magic smoke or who would win that contest. Hook up the audio feed to our onboard RCA jack. It would be nice if they had pads for a 3.5mm SMD connector on their audio board, perhaps in a future release. Turn that on, and voila! Color. I suppose you could run this in a cabinet and hook the HDMI output to a bystander monitor. It does take a while to dial her in because of our strange pixel clock, but it really is nice having this in color. I know it's sacrilegious to use LCD monitors, but I'm not a purist, so you'll have to forgive me. It does have a slightly different feel than a normal CRT because LCDs lack phosphor persistence. Okay, well, at least there's an easy way to add HDMI support without too much work, and we are lazy. For power, we've already tested running the logic off a 5V brick and also tested adding a 12V adapter for the amp using an onboard barrel jack. But we also need to test running off just 12V DC, and then finally off the cabinet's 16.5V AC feed. One thing we never did was to check how much current we're drawing. We should have done this already on the breadboard. I grabbed a bench supply with an OK current meter, fired up. Wow, only 0.7 amps. Can't believe it. The average active power consumption from the datasheets adds up to around 1.5 amps, so this is unexpected. I suppose we could have gotten away with a 7805 instead of the PSU-5A. I'm still going modern here, so let's add that PSU-5 switching regulator and run this on just 12V DC. We replaced the LM323 on our legacy board with a PSU-5, which is a TO3 replacement that doesn't require a heatsink. The PSU-5A was designed to replace a 7805 in the TO220 package, but at a higher current. I put a 5-volt dummy plug into the 5-volt jack so I don't accidentally crap myself. Plug in the 12-volt brick. Comes up just fine. These are really great. Nice and cool. Okay, that works fine with the onboard jack, so let's move the 12-volt DC feed to the control card, which simply feeds 12 volts into both pairs of AC connector pins. If you never plan on using this in a cabinet, then you can jumper out those rectifiers. I'm going to add them because we're going to test this in the cabinet. The voltage drop across silicon rectifiers is about 0.7 volts, so having them in there or not won't make a difference to the regulator or amp when running off DC. The last power configuration test is to run this in the cabinet, which supplies 16.5 volts center tapped AC to the connector. We'll just need to add the big filter, which is also okay to have in there for a 12 volt DC feed. Power that up again just to make sure everything still works. Didn't expect any issues with that either. Our PCB has 40% less surface area than the legacy board, which lowers the cost, but we'll need to add some rails to give it the same footprint. I created these in Fusion and printed them out. Put those on. Slide out the old card. Put that aside. Slide in our retro. You can recall from part 3 that I reworked this power tray for safety, added a circulating fan, and replaced some structural wood. This may anger some purists, but I also replaced the coin box with this panel to have a convenient power and coin button. Powered up, no smoke, yet. You would expect V unreg to be about 11 volts DC after the standard AC power conversion and rectifier drop, and we're pretty close. Monitor is warmed up. Looks like I need to make some adjustments, but she's putting out video. Drop a coin. The 1 credit lamp lights up. Second coin. Second lamp. The serve LED on this cabinet was burnt out when I got it, so that won't light up. Seems awfully quiet though. No hum like with the legacy board. Start a 1-player game and serve. Wow, great audio. I need to turn that down a bit. At least now we can easily adjust this. Try that again. I'll cut gameplay short here, but I will put out a separate video with a full game. I dropped the PCB manufacturing files, KiCad project files, and the source and binaries for the PLDs into GitHub. Everything here is protected by a strict beerware license. You can do whatever you want, just buy someone a beer responsibly. I will make a subsequent video to go over those widgets. I also want to complete something we talked about in that first video. Do at least a mental exercise to remove stuff to get as close as we can to the prototype chip count. Well, Ma, as you can clearly see, I finally got it done. I hope you all enjoyed this journey with me, first by breadboarding each section and figuring out how it worked, then by designing, building, and testing our own retro circuit board. Breakout has a unique and fascinating history as one of the last games designed in full discrete logic. No microprocessor, no code. From Bushnell and Bristow's concept to the prototype designed and built by Wozniak and Jobs, respectively, to the production engineering done by Gary Waters and the circuit board by Howard Canton. Amazing people that brought this game to life through their vision and talent 50 years ago. Thanks for hanging in there with me.